Our lesson for today is about the simplex method. We will start chapter 2, the simplex method. So what we have learned so far is the following. Now, we know that the solutions happens at extreme points. So, okay. We know that solutions happens at extreme points of the set of visible solutions, right? We learned that. So the optimal solutions happens at extreme points. So the method we present determines the extreme point in the visible solution in a particular order that allow us to find the optimal solution in a small number of trials. Okay, so the idea هنا simplex method works the following way. We know previously that the objective function will take the optimal solution at the extreme point of the complex set of visible solutions. So the idea is to list the extreme points, all of them, and substitute each one of them in the objective function. And then we find the maximum or the minimum. But this is not practical because we might have a lot of extreme points. So what we do, the simplex method will do the following. It will start at some extreme point, okay, and then it do some process. Then we move to an adjacent extreme point mujawara, such that the function takes a higher value at this new extreme point. Once we get there, we will do the process again. We will go to an adjacent extreme point for the new one, where the function will take a higher value there, assuming we are looking for maximum, and so on. So that means we will visit the extreme points in particular order and not all of them. So we are moving from extreme point to another adjacent and then to another adjacent, and the function is increasing. Okay, this is the way the simplex method works. Okay, so let's see. In this section we will consider problems in standard form only, in standard form. So we will work the simplex method in this section for the standard form. In the third section, which is section 2.3, we extend to arbitrary linear programming problems by developing a way of constructing a starting point. Okay, so in section 2.1, we will work with linear programming problems in standard form. If the problem is not in standard form, then we will learn how to work with that in section 2.3. And what is the difference? The difference actually that we don't know yet how to starting point. We need to construct starting point. If we are in a standard form, then we don't know how to choose the starting point. If we are in a standard form here, then we know how to choose the starting points, okay, the starting solution. What do I mean by starting point? I just said that the simplex method will start at some extreme point and then it moves to adjacent one, giving a higher value for the objective, and from there moves to a next adjacent one, extreme point, and so on, right? But we started at some extreme point at the beginning. So if the problem is in standard form, then we can find the starting point, the starting extreme point. But if it is not, then we don't know how to find the starting point, and we will learn that in section 2.3. Okay. Now, I can introduce the simplex method right away. I want to tell you Okay, let me say that the simplex method has some procedure. Okay, we make a table that looks like a matrix, and then we do a process which is similar to obtaining a reduced row echelon form of a matrix. Okay, and then that will take us to a solution. Now, how is that related to what I already said of moving from an extreme point to adjacent one and so on? So what I want to say here, that the process of the simplex method working with tables is easy, okay, and we can learn it. But why this process takes us to the optimal solution, we need to understand that. So I either start explaining how the simplex method is constructed and why it is true, why it takes us to the optimal solution. This is long. And then after we do that, we go and perform the procedure of the simplex method on examples. Or I go right away and perform the procedure of the simplex method on examples, so that I tell you how to work it out. And then we go back and explain why this process gives us an optimal solution, why the simplex process works for solving linear programming problems. So I would rather to go and work examples and tell you this is how the simplex method works. Okay? And after you get the hang of it, you understand how it works, then we go back and explain why this procedure is good, is true for solving linear programming problems. So let us move to examples right away. So I will go and pick an example. So let us go to example 2 in the book and just copy it and explain. Okay, now the simplex method is as easy as following. Notice it. We solve the linear programming problem in standard form. We have it in standard form, okay? In standard form by using the simplex method, which we will learn now. Okay, so this is the sorry. This is the standard, a problem in standard form. We have less than or equal in the constraints, okay? Now we convert it to what? To canonical form, okay? Now to do that, we add the slack variables here, x4, x5, x6. Now notice, actually, we are for the meantime assuming that the values here are positive. For the meantime, okay? Okay, now we introduce the slack variables, and then we convert that or make or form the following table. This is 1x1, 1x2, 2x3, 1x4. So it is 1x1, 1x2, 2x3, 1x4, and 0 for x5, 0 for x6. So this is the coefficient of the first row. It is in here. Okay? Again, the coefficient of the second row is in here. So notice what we have done in here. This is x1, x2, x3, x4, 5, 6. And below each one of them is its coefficient. Okay? And the third equation, so we have coefficient 6, 6, 6, 6, 2, 0, 0, 1. This is the way 662,001, and then we have in the objective in this column we have 8. Okay, now in the last column we have the following. Notice here we can write this as z minus 8x1 minus 9x2 minus 5x3 equals 0. So now we move this to here, to this row, which we call the objective function. So it is negative 8 as coefficient of x1, negative 9 coefficient of x2, negative 5 coefficient of x3, and 0 coefficient of x4, 0 coefficient of x5, and 0 for x6. And we have here equals 0, this equality here. Okay, so this is called the objective. We will call it the objective row. The objective row. Okay, now what is happening here? Now we know how we chose the rows. Okay, now let me clean all that. Now, why do we have to the left? Why do we have x4, x5, x6? These are the slack variables. We will take them to be the basic variables. You remember the basic and the non-basic variables? We will choose here the slack variables x4, x5, x6 to be the basic variables. Okay, basic variable. And the other variables x1, x2, x3, x4, these are non-basic variables. We will choose them to be the non-basic variables. Why are we doing so? The non-basic variables, we will make them all equals to 0. Remember that? Okay, these are the basic variables, and now all these things together. Now if I make this equal to 0, this equal to 0, this equal to 0, what I get? x4 equals 2. Now these are zeros, x5 equals 3, and these are zeros, x6 equals 8. So I get an initial solution, which is 0, 0, 0, 0, and 2 for x4, 3 for x5, 8 for x6 transpose. And this gives me an extreme point. So truncating this, I will get the first extreme point, which is 0, 0, 0, the origin. So this is the first extreme point, or the starting. Okay, this is the starting, which means we stand at this point first, at the origin. Now we want to move to another extreme point. Now this is the idea of the simplex method. Okay, so the slack variables are the basic variables. The non-slack variables, the original ones, are zeros. That gives me the origin as the starting point. Now I want to move to an adjacent extreme point. What do I mean by adjacent extreme point? I want one of these zeros, the 4 zeros, to be not 0. Okay, that means I want one of the variables x1, x2, x3, x4 to convert it to not 0, and at the other hand, one of the variables x5, x4, x5, x6. So no. Did I say I have too many variables here? Okay. So I added one more coordinate. Let me erase that. Only I have 1 0 only. So I will take this here. So I will have x1, x2, x3 are zeros. Those are the, okay, so I need also to erase that. Did somebody, okay, Dr. Udar, thank you. I did not notice this. No. So no notified me to this, but I did not pay attention to her. Okay, this is the way. Okay, I am recording the lecture one. Okay. Okay, good. Now, this is the origin, and it is the first extreme point. I want to move to another extreme point, to adjacent. Adjacent means I will change one of the variables, x1, x2, x3, to be not 0. And at the other hand, I will change one of the basic variables, x4, x5, x6, to be 0. So one of the non-basic will be made non-zero, and one of the basic will be made 0. This is what we mean by adjacent. Okay, how we do that? Now let's go back. This is why x4, x5, x6 are here, because we chose them as basic variables. Okay, now the idea, I want one of the basic variables to take it away and consider it not basic anymore, and one of the non-basic variable to make it a basic. This way I will be moving from an extreme point 0, 0, 0 to another, to adjacent extreme point. Adjacent means taking one of the basic variables to convert it to be non-basic, and bringing one from non-basic to make it basic. We will then move to an adjacent extreme point, and the value of the objective function will be improved. How we do that? Okay, so these are the basic variables for now. One of them will be changed. Which one of them will change? Okay, I will show you. Now let me go back here and clean this. We want to cancel or omit one of the variables, x4, 5, or 6. How we do it? We want to replace it, to place one of them with one of the variables, x2, 1, 2, 3. How we do it? Okay, notice the way we do it. We go back to the objective row, this objective row, and choose the smallest negative value, which is -9. So I choose -9 because it is the smallest here. So I want to work with this column. And now this row means I am entering x2. This is called the entering variable. Entering a column, okay? Entering variable or column here. Let's call it variable. So why I chose it? Because the smallest in the objective function is here. So I will take this column. If we have two numbers that are equal and they are the smallest, we choose one. Okay. Now I chose a column, which is x2. x2 now will become a basic variable. So I want to take one of the basic variables and make it non-basic. Which one I choose? Which means which row I choose. The way I decide is the following. We will divide 2 over 1, which give us 1, and divide 3 over 3. Sorry, this is 2. 3 over 3, we get 1, and divide 8 over 6, which is something 4 over 3. Now I got here 2, 1, 4 over 3. I will take the smallest one. Okay, so I will choose the smallest. So the smallest came to be here. So I will choose the second row. So good. I will choose the second row. Okay, now this will be the departing variable. which means I want to make x5 non-basic, to convert it from basic to non-basic, and so it is departing the basic set of basic variables, and make x2 from non-basic to basic, so it is entering the set of basic variables. Okay, good. So this is how we choose which column and which row, which variable to enter, which variable to leave. Now let me go and clean all these things. Now what we do? Now we work as the obtaining the reduced echelon form of matrices. Okay, so what we do? We chose 3. Now you know why we chose 3. Make it 1, divided by 1. So divide the whole row by 1. So we get, divided by 3. Make it 1, divided by 3. So it is here now. It is 1. Divide this by 3. It is 2 over 3. 4 over 3. This is 0. 1 over 3. It is here. This is 0. And 3 over 3. Divide everything in the row. Okay? Good. Now what we do? We want to make this to be 0, and this to be 0, and this to be 0. And you know how to do that using row operation, right? So just working as in matrices. Now we will make them zeros using the new row. So we are using this row now. How to use this row? Now notice here x5 has left now, and we have here what? x2 in place of x5. Now to make this one here to be 0, we multiply this by -1 and add. So multiply the whole row by -1 and add it to the first row, so we get that. Okay, now to make this 0, we multiply 1 by -6. So multiply the whole second row by -6, the new one in the second table, and add it to the third row, then we get this row. Now to make this 0, we multiply 1 by 9 and add to the last row, then to make this 0, we get that. So multiply the second row, the new one, with 9 and add it to the third row, all of it. For example, if we multiply this with 9, we have 9. Add it to 0, then we have 9. Okay, good. So you know how to get that. Good. Okay, now we will repeat the same process again for this new table. So let me clean. And there will be a departing variable and an entering variable, and that depends on what? And the same thing. Now where is the most negative, the smallest negative in this row? It is here. It is 2. So this is the smallest. So we will choose this to be the entering variable. x1 will be entering variable. Which row we choose for the departing variable? We do the same. Divide 1 over 1/3. We get 3. Divide 1 over 2/3. We get 3 over 2. Divide 2 over 2. We get 1. So this is the smallest. This is the smallest happened here. So we will take this row, and therefore x6, the row of x6 will be the departing. So x6 will go away. Okay, now we'll do the same thing. We will convert this 2 to be 1. Okay, and use that to make reduction, row reduction, which means we want this to be 0 using the new row here. So we have the new row. First, we divide by 2 so that we make this this 2 here, we make it 1 here. So we divide by 2. You know all this. So divide the whole row by 2. Notice we have x1 instead of x6 here. x6 has departed the set of basic solution, and x1 has entered the set of basic solutions. Okay, now use this new row below here to make the entries in the above zeros, which means row reduction. So I multiply this by this row, I multiply it by negative 2 over 3. So let me clean that now. So I want to make this 0. So I multiply the row below there with negative 2 over 3 and add to the row above it, okay? And to make this 0, I multiply by negative 1 over 3 and add it to the first row. To make this 0, I multiplied by 2 and add it to the objective row, the last one. Then we get this final table. And we are done. Why we are done? Because there is no negative values in the objective row. There is no negative values in here. All of them are zeros or positive. Then we are done. So we are done. What do I mean by we are done? We got the optimal solution. Oh, okay, how? Here we go. Now x1 equals 1. x2, see here is x1, x2 is 1 over 3. Okay, now x4 and x4 is 2 over 3. Here we go. This is x1, x2, x4. And what's about the remaining? They are all zeros. And this is the optimal value of z, and we are done. Thank you. Okay, and actually what we have done is moving from 0, 0, 0 to where? So we moved this in here. We started at 0, 0, 0, and then we moved to what? x2 now is what? Is 1. So 0, 1, 0, and then we moved to what? Make it bigger so that at this table, move to what? Okay, x2 is 1. Then we moved, I believe now to 1, 3, 0. Okay, and we got the optimal solution here, which makes z equals 11, right? Compute that. Z is above there. What z equals? Z equals 8 times x1 plus 9 times x3 plus 5 times x2 and x3. This is x1, x2, x3, and then we get 11. Okay, good. So we moved from extreme point to an adjacent one. Okay, and then we got the optimal solution. This is the simplex method, easily, very easy. Yes, it is that easy. But you still don't know why this works and gives optimal solution. Since the beginning of the semester, we learned many things. And I used to say that these things will be put together to make the simplex method. So how this procedure, the one we have done here for this example, is related to what we have learned. Actually, what we have learned will explain why this procedure gives the optimal solution. And we will come back to this, okay? I wanted to start it with such a thing, but that will be boring for you. So I wanted to work the simplex method, the procedures, and then go back and explain why it works, why it gives the optimal solution. And before we go to that part, let me work two more examples. So let me take this example here. Okay, another example. Oops. This is big. Let me make it small so that we can see it in all of them in a screen. Maybe this is good. Okay, this is good. Maybe. Okay. Consider the linear programming problem. Again, this is in standard form converted to canonical form, and then we get that. Again, we have the first row here 1, negative 1, negative 1, and then 0, 1, 0 with the slack variable. So 1, negative 1, negative 1, 0, 1, 0, and 0 for x7. And this is 2 here. Okay, again we will have negative 2, 5, negative 3, negative 3, 0, 1, 0, 10, and it is here. Okay, and now again this is the third row. Okay, and where we get the objective row, this is again the objective row where we get from. This is z minus 2x1 minus 3x2 minus x3 minus x4 equals 0. So this will gives me negative 2, negative 3, negative 1, negative 1, 0, 0, 0. Okay, good. So we got the table. Now let us work what we have learned. So let me clean that. And notice here the basic variables are x5, x6, x7. The slack variable, they are the slack variables. Okay, x5, x6, and x7 are now taken as basic variables. Okay, now we want to make one of them depart and enter one of the other variables, x1 to x4. How we do so? Again, we go to the smallest value in the smallest negative value in the objective function, and then we keep doing so till the objective row has no negative values. Then we are done. If this works. What do I mean if this works? Okay, now negative 3, so this will be the entering variable, which is x2. Again, I will divide 2 over negative. I will not take the negative ones, so I will not work it out, because I will take the smallest positive integer in such a case, and I will not take this one. Okay, so I have only one choice, which is dividing 5 by 2 by 10 by 5, which is 2, and that will tell me that I will choose this row, and the departing variable will be x6. Okay, So now if you notice here, x6 has gone and we have x2 instead. Now again, do the row operation, make this 5 1, divide everything in this row by 5 and do the row reduction for the whole table. So we get here the new row. Now use this row to make this here 0, and to make this 0, and to make this 0, and do the row operation, and we got the zeros here and here and here. Good. And we got now entering variable. We're done. x6 has left, departed, x2 has entered. Now we will do the same thing for the new table. Which one is the smallest? This one is the smallest, right? So we will take x1 to be the entering. What about the departing? We have only one choice, which is 4 over 3 over 5. We don't use that. This is 2 over negative 2 over 5. This is negative, so we will not use it. 15 over 0, we will not take it. We will take the smallest positive. So we have only 4 over 3 over 2. We don't have to compute it, it is the only one. So this is the departing variable. So let me clean all that. So again, this is the departing variable. Okay, good. Now this 3 over 5, we will circle it and make it 1. Here we go, it is 1 here. So divide everything in that row by 5 over 3. Then we get this new row here. And now use this new row to make all of these, this one here and this one here, to be 0. Right? They are 0 now. Row reduction, row operation. Okay, done. So we got the new table. We will repeat the same process again, but we will not be able to do so. We will not be able to repeat the same process. Why? Because if you look at the smallest negative value, it is this one. Right? So we will think to choose x3 to be the entering variable. Right? But now, once we want to find out which one is the departing variable, then we divide this over negative, so we will not take it. Or we go divide this over what? Negative, we will not take it. Divide this over what? Negative, we will not take it. Okay? Which means that x3 can take any number. So the most negative entry in the objective is this. However, none of the entries in the bivotal column. So this column is called bivotal column. Okay. None of the entries is positive. None of the entries is positive. So we conclude that the given problem has no finite optimal solution. You can make the solution as big as you want by increasing the value of x3. x3 is unbounded because of that. So we stop. No finite optimal solution. Why? All these are negatives. Okay, all of them are negative. Is that clear, or I just missed things up? Okay, just highlighted one time. Okay, all of them are negative. Okay, so this is the simplex method. Let us work 2 more examples, and then I go back and explain why this method works. Actually, yeah, let's work more examples. I was thinking not to work examples and to leave that for tomorrow, because tomorrow we will have a lab, a tutorial. But let us go to the book and take example 20. I have computed that actually, but I want you to compute with me. Maybe I did some mistake. Okay. Now we want to use the simplex method to maximize this. Okay. So we will make a table. But first we need to introduce the slack variables, right? So in here we will have 2x1 plus x2 plus 3x4 plus 3x3 plus x4 plus x5 equals 8. So this is the first slack variable. Now, okay, this is here and this is here. 2x1 plus 3x2, 2x1 plus 3x2 plus no x3 plus 4x4 plus, here let me see, plus x6 equals 12. Change this. 3x1 plus x2 plus 2x3, no x4, no x5, no x6 plus x7. This is the slack variable 18. So these are the slack variables and they are the basic variables for us. Okay? So the basic variables are x4, no, x5, x6 and x7. The non-basic variable are x1, x2, x3, x4, and we make any one of these to equal to 0. And now if we make that equal to 0, this will be 8, this will be 12, right? This will be 12, and this will be 18, correct? So this is the initial solution we have, okay? And the first extreme point is 0, 0, 0, 0. So let us make the table now. So we will have x1, x2, x3, x4, x5, x6, x7, and then this column is left for, do I need to make columns? Okay, just no column, the very last. So we have okay, so we make this column here and this column here, and we will have this to be x5, x6, x7. Okay, so I will do that. I will try to make my lines straight. Okay, this will be 8, this will be 12, this will be 18. Boom. Okay, now the first equation, I will have 2 for x1, 1 for x2, 3, 1, 1, 0, 0. The second equation, 2, 3, 0, 4, 0, 1, 0. The third equation, 3, 1, 2, 0, 0, 0, 1. I need now to make the objective row. Okay, the objective row, how do I make it? This is z minus x1 minus 2x2 minus x3 minus x4 equals 0. So I will go for minus 1 for x1, minus 2 here, minus 1, and these must be zeros because they are the basic variables, and this is 0. Okay, so this is the objective row. Okay, good. So we have the initial table. Good? Okay. Now we need to find the entering variable, the departing variable, the bivotal column, and I need to use these words so that when I use them, when I go back and explain why the Simplex method is true, then I will find, okay, bivotal column, bivotal row. Okay, we need to find the bivotal column, the bivotal row, and the bivot. What do you mean? Okay, again, we go to the smallest negative value in the objective row, and then we take that column. This is now the bivotal column. This is the bivotal column. Okay, now we need to choose, let me not write too much in here, let me choose the theta ratios. Theta ratios, what do we mean by theta ratios? This is 8 over 1, okay, which is 8. In here 12 over 3, which is 4, and in here 18 over 1, which is 18. So this is the smallest one. Okay, so we take it. So what we get here, this is the bivotal row. This is the bivotal row. Okay, now again, this is the entering variable. Oops, the entering variable, which is x2, and this is the departing variable. The entering variable and the departing variable. Okay, good. And now this 3 here we called the bivot. And the whole process we are doing is called bivoting. So we will be doing bivoting, which means obtaining the new table as we have done before. Okay, so we will do row operations. So again, we will write that x1, x2, x3, x4, x5, x6, x7, and now we will have here x5, x2. So we'll have, instead of x6, x2, and here x7. Okay, and now the second row will be replaced by divide everything by 3 so that the bivot is 1, and this will be 2 over 3, this will be 0, this will be, so we are dividing everything here by 3, right? So you don't have to write that in your solution this way, but I am here just explaining. So let me remove them. Divide by 3, so I get 4 over 3. So let me spot this correctly. And under x5 I get 0. Here I get 1 over 3, I get 0. And 12 over 3 is 4. Okay, now I want to make the 1 over the pivot to be 0. So reduction formulas. So help me if I am wrong. Do you mean Asma x6? No, we have here, this has to be x2, not x6 now, because x2 is departed. Or you mean x6 must depart. Okay? Okay, to make that 0, multiply by -1 and add, we get 0. Multiply by -1, -2 over 3, add it to 2, which is 6 over 3, so we get 4 over 3. Am I computing correctly? Okay, multiply 0 by, we get nothing, add it to 3. Multiply 4 over 3 by -1 and add it to 1, so we get -1 over 3. This we get nothing. Multiply this by -1 and add in here. You multiply this by -1, it is -4 over 3, and we have by -1, sorry, by -1 and add it to 8, so we get -4 added to 8, we get 4. Okay, now multiply by -1 and add to this to make it 0 again. Multiply 2 over 3 by -1 and add it to 3 over 3, so we get 7 over 3, because 3 over 3 is 9 over 3. Multiply 0 by negative and add, we get nothing. Multiply this by -1, so -4 over 3, and multiply this by -1 and add to 0, we get nothing. Multiply this by -1, we get that, -1 over 3. Multiply this by -1 and add. Now multiply this by -1 and add to 18, we get 14. Boom. Okay, we are not done yet. We need to work that for the objective row also. Okay, let's see. We multiply 1 by 2 and then add to get rid of that one, so we get 0. So multiply this by 2, we get 4 over 3, add to -1, so we get 1 over 3. Multiply this by 2 and add, we get -1. x73 equals 0. What do you mean, Siham? x73? Make it clear, please. What do you mean? Okay. Now multiply 4 over 3 by 2 and add it to -1. We get 8 over 3, -1 over 3, so 5 over 3. Multiply this by and add to that, we get 0. Multiply this by 2, 2 over 3, add to 0, and multiply this by 2, we get 0. 2 over 3, 0. Multiply now 4 by -2 and add it to 0 by 2, not -2. Add it to 0, we get 8. Boom. Okay. Okay, let's look at the objective row, the new objective row. We have a negative value in here. It is the smallest one. So this is our bivotal column. And this is the entering variable. Okay. And now divide 4 by 3, we get 4 over 3. And here divide 1 by 2, we get 1/2. Okay, so 7 Siham, it means 7, maybe Siham means we will replace x3 with x7, maybe. So we will take this. So we don't divide over 0, right? So we divided 4 over 3, 14 over, what did I do? This is 14. 14 over 2, which is 7. So I will take that one. No, I will take this one. Yes. So this is the bivotal rule, bivotal rule, and this is the departing variable. Okay, and this is the bivot, and we will do by voting again to obtain the new table. Okay, more row reductions. So I will go to x1, x2, x3, x4, x5, x6, boom, x7, and now I will change the x5 to be x3. I already have here x2 and x7 is still here. Okay, now let me take the numbers. So 3 over 3, divide everything here by 3, I get 1, I get 0, I get 4 over 9. Am I correct? I get negative 1 over 9. I get 1 over 3, negative 1 over 9, 0, 4 over 3. Good. Now this is already 0, so we change nothing to it. So I will copy this row, 0, 1, 2 over 3, 4 over 3, 0, 1 over 3, 0, 4. Okay, boom. I want to make this 0 now, so multiply by negative 2 and add, then I get what? 0, multiply by negative 2 and add, it is 0 and 0, negative 2, negative 8 over 3 plus 7 over 3, I get 1 over 3 here. Multiply by negative 2 and add, I get 2 over 3 minus 4 over 3, so I get multiply 2 by, so I get, sorry, multiply negative 1 over 9 by 2. What did I do first? I need to make sure, I think I did not compute this correctly, because I must multiply 4 over 9 by 2 and add it by negative 2 and add it to 7 over 3. Multiply 4 over 9 by negative 2, I get negative 8 over 9. And I have 7 over 3, which is 21 over 3 over 9. And 8 and negative 8 over 9, so I have 13 over 9. Okay. Now multiply negative 1 over 9 by negative 2 and add to negative 4 over 3. So I get negative 2 over 9 plus negative 12 over 9. I get negative 2 times negative 1 over 9, I get 2 over 9 plus negative 4 over 3, which is negative 12 over 9. So 2 over 9 and negative 12 over 9, so I get negative 10 over 9. Oops, okay. Now 1 over 3 multiplied by negative 2, negative 2 over 3 added to 0, I get this, negative 1 over 9 multiplied by negative 2, I get 2 over 9 added to negative 1 over 3, which is negative 3 over 9. I have negative 2 over 9, so I have negative 1 over 9 here. And in this one I had nothing, it is, in this one I get, I had 0 there, right? This one is 1 here, yes it is 1. So I would have this to be 1. And negative 2 by 4 plus 14, I get 6, right? I did not divide something. was supposed to divide that by, okay, negative 2 times 4 over 3, which is negative 8 over 3, plus 14. 14 is 42 over 3, negative 8 over 3, and 42, I get 34 over 3. Boom, let's keep going. To the last row, I multiply, just add. I will add the first row here to the last row there. I get 0 because I want to make the negative 1 to be 0, right? So I just add that to that. I get 0 in here. I get 1 over 3, 4 over 3, which is 3 over 9 and 4 over 9. And this is 7 over 9. Negative 1 over 9, 5 over 3, 15 over 9, negative 1 over 9, 14 over 9. Alright? Okay. And I add this and that. I add this and that. 2 over 3 plus negative 1 over 9, which means 6 over 9, 5 over 9. Now add this to that, boom. Okay, now 4 over 3 plus 8, 24 over 3, 28 over 3, because 8 is 24 over 3. Boom, we are done. Now if you look at this row in here, the objective row, there are no negative values in the objective row. Therefore, we have reached an optimal solution to the problem. What is the optimal solution? Let us see. This is x3 and it equals 4 over 3. So x3 equals 4 over 3. And what else? x2 here and here is 4. So I have x2 equals 4. And what else? x7 equals 34 over 3. Okay. And the remainings, x1 is 0, which is the same as x4 and x5 and x6. Now the value of z, this is here the maximum value of z, which means z, like this solution here, all of this solution gives that z equals 28 over 3. This is the maximum solution. So actually we will not take the slack variables in the solution. So finally we will say, because our original variables are x1, x2, x3, x4, and the solution where x1 is 0, x2 is 4, x3 is 4 over 3. So this is our solution, and that gives z equals 28 over 3. Let us make sure this is true. Do we really get z equals that? I want to take z. Z is x1 to x2, x3, and x4. Z equals this, x1 plus 2x2 plus x3 plus x4. Compute that. Substitute. If we substitute here 4 and substitute here 4 over 3, is that correct? Yes. This will be 8 which is 24 over 3, and this will be 4 over 3, and then we get 28 over 3, which is this. So we have reached optimal solution. We used the simplex method. Okay. Now another exercise which will lead us to have no solution, because we will have something similar to the examples where the column which has the least negative value in the objective row, so going to the least negative value in the objective row and take that column, then we will find the entries of that column, all of them are negative or zeros, so we cannot continue, which means there is no optimal solution. And this will happen in exercise 22. So let us copy that. Let us go to the book and bring exercise 22 here. Okay, exercise 22. So let us do it for a quick. I will abbreviate so quick. So we will have two slack variables, right? So we will have x1, x2, x3, and now the slack variables are x4 and x5. So we'll have here x4 and x5. So I will do that for a quick, because you know how we obtained, how we get all of that. And then here we get 6 and 15, and then we get -1, 2, -7, 1, 0, and 1, 1, -3, 0, 1, and here we get 1, right? -3, -1, 0, 0, and 0. Okay, now this is the bivoidal column, this is the entering variable. Now we have 6 over 2, which is 3, and here 15 over 1, which is 15. So this is the smallest. So this is the departing variable and the bivoidal column, and this is the bivoid. Okay, so now let me make another table again. x1, x2, x3, x4, x5. Now this will be 1 here, right? Divide by 2, -1/2, -7 over 2, 1/2, 0, and 3. Now this will be x2 instead of x4. We'll have x2, and this is x5. Now make that 0, just make it 0. Let me copy it from here. Multiply it by -1 and add. So we'll have here, what do you have? Yes, this is, sorry, this is -1/2. Let me fix this. Oops, -1/2. Okay, so do your computations. That will be 3 over 2, 1 over 2, -1 over 2, 1, and 12. Make sure these things, I computed these things correctly. Now, this will be -23 over 2, -1/2, 3 over 2, sorry, oops, we must make that 0, right? -23 over 2, 3 over 2, 0, and 9. Boom. Okay, again, Let's do by voting again. So this is the most negative, so we'll take this as the entering variable. And now if we divide, we not divide over this because it is negative, we will just have one choice, which is this. Okay, so we will divide by 1/2 the second row. So my lines are so bad, I'm using the writing tablet. Okay, I shall wait and make the second row to be here 1. Okay, let me make it in blue. So we have x2 here, and x3 will come here in place of x5, right? And we'll divide by 1/2. We get this, and then we get that, and then we get this. Divide by 1/2, and then we get 3. Okay, so we divided by 1/2. Now row reduction. So we get 0, 1 here, 10 here, and -3 here, and 7, and then 91. And I made this computation quick before the class starts, and also okay, no, we are done. Now we go to the objective row and make them 0, and then we get I believe 68/2, 0, 0, -10, 23, and here somewhere 23 times 24/2 plus 9. I did not compute it, because what we will do, we have 24, right? And then we want to multiply it by 23/2 and add it to 9, yes. Okay, now we look at the objective row. We have -10 in here. This is the smallest one. So we are thinking to take this as the pivotal column, and this to be the entering variable. We will not be able to do so because we have negatives here. In this column we have negatives here. So that means this makes us conclude that there is no finite optimal solution. Why is that? Because the more we make x4 grow, the bigger the value of the function is. Okay, good. So why the simplex method gives us optimal solution? Why all these things, all these procedures that we have already learned, the ones I showed to you, they do really give us optimal solution for the linear programming problem. And how these procedures are related to what we have learned before about extreme points, about convex sets, about basic solutions, and so on. We learned before that an optimal value of the function, maximum or minimum, will happen at an extreme point. So this is the first thing we learned. So the simplex method will keep moving from some extreme point that we choose. We might not be able to choose sometimes according to what we have learned so far, but we will learn how to choose it for all forms of linear programming problems. Okay, and then we keep moving from an extreme point to an adjacent, and then evaluate the function, and then move again from an extreme point to an adjacent and evaluate the function till we are done, which means that there are no negative values in the objective row. Now, if you notice here what was happening, we started with the following value of the objective function with 0, and then we moved to an adjacent point. So actually the adjacent point here, the extreme point here for this one was 0, 0, 0, 0 for x1, x2, x3, x4. Then we move to another adjacent point where the value of the objective function increased, and that objective point, what happened, we replaced x4 with x2, and x2 now is 4. Okay, so the adjacent extreme point to this one is 0, 4. We removed what, x6, not x. We removed x6 and replaced it with x2. Now one more step. Now repeating the process again makes us reach this maximum value of the function by removing x5 and replacing it with x3 and make x3 equals that. So this is another adjacent, another extreme point which is adjacent to the previous one. So from here we move to adjacent to it, and from this one to this we move to another adjacent, and we got the extreme value of the function. So moving from extreme point to another adjacent. This is what the simplex method is doing. And every time it moves from an extreme point to an adjacent, it maximizes the objective function. And then we stop when the entries in the objective function are all positive. Because since by doing this, then we convert the non-basic variables to basic variables, but one at a time. This is the adjacency. Changing the set of basic variables, throwing one away, and like start with set of basic variables, throw one away, and bring one in place of it. Okay, so we have a new set. The new set and the old one before we throw away, they are called adjacent solutions. Okay, so let's go to there. Now you know the motivation behind everything that I will explain now, which I will show to you in detail. And we will go kind of quick over these because I have already explained this to you through working the examples. Now we want to learn why the simplex method works and give us the optimal solution. Okay, go down more. Oops, what I did. Okay. Okay, the simplex method. Okay, good. So start with the standard form. Here we go, the standard form. And we are assuming b is greater than 0 for a while, and then we will take the cases where b can be, entries of b can be negative. So make the canonical form, then you know that we obtain this matrix. Correct? Okay, good. Now, this matrix here remember when we have a standard form, and then we make canonical form. We make the canonical form introducing slack variables. So here the S is the convex set of visible solutions. Okay, here we will call it S prime, the convex set of visible solutions. You know, when we get a visible solution in the canonical form, we truncate the slack variables, the coordinates that correspond to slack variables, and keep the original ones, and then we get a visible solution for the standard form. Okay, so if we denote S prime to be the convex set of the solutions in canonical form. Okay, now what do we want it here? An definition. An extreme point in S prime, two extreme points, distinct extreme points, two distinct extreme points are called adjacent if, as basic visible solutions, they have all but one basic variable in common. يعني if we start إذا بدأنا بالأول وكان في عنده البيسك فاريبلز، مجموعة من البيسك فاريبلز في داخله، فشيل البيسك فاريبل خليه يصير نون بيسك، وهات واحد من النون بيسك خليه يصير بيسك. اوكي، بيكون الأصلية وهذه بيكونوا adjacent solutions. جميل جميل. يعني مثلا شوف هذا عندنا solution هنا 0 0 8 15 هو adjacent لهذا اللي تحته. ليش؟ ايش اللي صار؟ هنا كان مين البيسك فاريبلز؟ هنا كانوا البيسك فاريبلز u و v، اما x و y كانوا نون بيسك لانهم اصفار. لكن شو صار عندنا هنا؟ الواي صارت بيسك والفي ما زالت بيسك، وهذه صارت نون بيسك نون بيسك. فبالاول ايش كان عندنا؟ يو وفي بيسك فاريبلز، اكس واي لا. فرحنا خلينا اليو تصير نون بيسك وجبنا مكانها الواي تصير بيسك، لذلك صاروا الاثنين adjacent. جميل. وايضا لو رحنا على هذا هيك كمان adjacent مع الاول. ليش؟ لانه صار عندنا البيسك فاريبلز هم y ومين؟ ويو. انا كان عندي يو وفي بعدين خليتهم واي ويو. انا شو عملت؟ شلت الفي خليته يصير نون بيسك من الاول واستبدلته بواي. جميل. وايضا هذا adjacent مع الاول. ليش؟ بكون انا شلت اليو صار نون بيسك استبدلته في مين؟ في الاكس. اذا خلينا نشوف بالرابع هذا البيسك فاريبل مين هما؟ اكس وفي. بالاول البيسك فاريبلز مين هما؟ يو وفي. اذا انا ايش عملت؟ كان عندي يو وفي، شلت اليو واستبدلته في اكس فصار عندي في واكس. اذا اللي كان عندي بالاول، وهذا adjacent. اوكي، لكن لاحظ بانه الاول ليس adjacent مع الاخير. الاول اليو والفي هما البيسك، الاخير الاكس والواي اثنين تبدلوا. شلنا اثنين ما حطينا مكانهم اثنين، ما بصير حتى نقول adjacent. بدك تقول adjacent انت بتشيل واحد نون بيسك وبتجيب واحد نون بيسك مكانه بتساويه بيسك. واحد بقى بتشيل واحد من هنا بتجيب واحد بداله، مش يشيل اثنين وتجيب اثنين بدالهم وبطلوا يصيروا adjacent. اوكي جميل. الان التسلى فيهم، شوف مين كمان adjacent مع مين. يعني لو انا عملت اصفر مثلا، هذا طيب هذا adjacent مع مين؟ اوبس وين رحت؟ شو هذا؟ ارجعه مثل ما كان، انا بديها. طيب قولوا لي هذا adjacent مع مين؟ مين يعطيني هذا adjacent مع مين؟ يعطيني واحد من اللي فوق. حد يجاوبني؟ هندول if you want to write the row operation just write على اليسار مثل ما تعودتوا بالجبر 3 times row 1 divided by 3 plus row 2 whatever the way you learn no problem. اوكي مين يعطيني مين adjacent مع هذا؟ اعطيني اي واحد adjacent مع هذا. هنا كان عندنا x و y اي واحد صحيح كلهم adjacent له ما عدا الاول كلهم adjacent له 0 5 7 2 0 نعم. هنا في الاخير عندنا x و y وفي هذا اللي علمناه في اصفر عندنا y و u فبكون شلنا الاكس حطينا مكانه اليو اذا هذول adjacent. هذه هي الفكره هذا اللي كنا نعمله لما كنا نجد البايفويتال رو والبايفويتال كولوم والبايفويتال رو ونروح نبدل هذا من بيسك نسويه نون بيسك ديبارتنج وهذا انترنج نسويه بيسك. فكنا فعليا بننتقل من اكستريم بوينت تو ان ادجيسنت اكستريم بوينت وكل مره بننتقل بنقيم الفانكشن الاوبجكتيف فانكشن. هيك كانت تشتغل السمبلكس رول. مثلا بدأنا عند الزيرو هنا راح تشوفوا المثال بعد شوي. نبدأ عند الزيرو بننتقل إلى adjacent point أخرى extreme point هذه adjacent ومنها بننتقل إلى هذه هسه بتشوفوا. فبنكون انتقلنا من 0 0 لوين؟ لعند 0 3 0 وبعدين لمين انتقلنا؟ ل 3 over 2 5 over 2 هذول بيمثلوا لنا adjacent. هيهم هذا adjacent مع مين؟ مع هذا كويس. بعدين هذا adjacent مع هذا صح؟ لأنه خليني أشوف اللي معلمين بأصفر. خليني أنظف هذه الأشياء كلها. شوفوا ونظف هذه الأشياء. أوكي صرنا منظفينها مرة أخرى. الزيرو زيرو adjacent مع 3 0 ليش؟ أعلمهم باللون الزهري. أوبس أعلمهم باللون الزهري. هذا adjacent مع مين؟ مع هذا صح؟ جميل. والآن باللون الأصفر هذا نفسه adjacent مع اللي تحت فصار المحترم هذا adjacent لهون. فصار عندنا الانتقال اللي أنا مسحته هون خربشت عليه. فصار عندنا الانتقال التالي من 0 0 بعمل evaluation للفانكشن بعدين 3 0 بعدين 3 over 2 5 over 2. كل مرة بنتقل بعمل evaluation للفانكشن. الايفالويشن هذا كان يصير معنا في الكورنر اللي تحت لما نعمل الرو اوبريشن تتغير القيمة كانت 0 بعدين صار قيمة أخرى بعدين صار قيمة مختلفة بنكون وصلنا أو لسه. أوكي جميل. الآن شو عملت أنا؟ كمان طلع فوق كمان يا إلهي خربطت الأمور هنا شوية. شو عملت؟ دول كانوا خشين فوق بعض. أوكي الله بيعينكم لما أبعث لكم إياها. هذه مكانها تحرك لو بدي أرجع أرتب الأمور. This has to go. أنا ما لازم أضغط على الصورة هي لأنها تتحرك. أوكي لكني بنسى بعض الأحيان. وهنا كان هذه 3 over 2 5 over 2. إذا أنت حاب تفهم شو اللي بيصير هذه الطريقة بتشتغل فيها السمبلكس ميثود. أوكي الآن هذا كلام خلينا نشوف. Simplex method invented by this guy and proceeds from a given extreme point to another adjacent extreme point so that the objective function is increased. هذا اللي أنا قلته. So the simplex algorithm consists of two steps. For a way of finding out whether a given basic solution is optimal ولا لا. If it is not optimal, we go to the adjacent visible basic solution. فإذا كان الأوبجكتيف رول اللي تحت فيه ما فيه نيجاتيف خلاص وصلنا. إذا فيه نيجاتيف بنكمل عشان نروح على الادجيسنت اللي بعديها. أوكي. والآن عشان أستطيع أشرح إيش اللي بدي أعمله تحت هذا الكانونيكال فورم مرة أخرى. فلاحظ إيش عملنا إحنا هنا. خلينا السلاك فاريبلز ياخذوا القيم هاي. وكانت هذه بالنسبة لنا الستارتنج بوينت. إذا الستارتنج بوينت كانت عندنا 0 0 0 حتى نوصل لعند slack variable B1 B2 إلى BM، وكان هذا السلاك فاريبل الأول وهذا السلاك فاريبل الثاني وهكذا، وهذا XN هذول اللي non basic variables لكنهم ال original variables. إذا هذه هي الستارتنج بوينت إلنا، starting point، واحنا قدرنا نعمل هيك لأنه كان عندنا standard form. اوكي من الستاندرد من الستارتنج بوينت ايش رايحين نعمل؟ رايحين ناخذ الزي مثل ما انتم شايفين ونكتبه بالطريقه هذه، ماشي؟ وهيو هذه الطريقه اللي استخرجنا فيها ايش؟ الاوبجكتيف رو. طيب ومنين جبنا الانترز الاخرين؟ الانترز الاخرين هم جبناهم من وين؟ هذول المحترمين، هذه المصفوفة كلها هي مثل ما انت شايف صفطناها هون تصفير، تمام؟ ومين البيسك فاريبلز مبدئيا اللي هم السلاك فاريبلز، تمام؟ اوكي، وهذا الصف العمود الموجود هنا بالكونسترينت. اذا هذا اللي حركة اللي احنا عملناها. بعدين ايش بدنا نعمل؟ We are now ready to describe the steps of Simplex method that are used repeatedly مثل ما عملنا. اوكي. Now the value of z can be increased by increasing the value of any non-basic variables with negative entry in the objective row. احنا كنا نروح على الرو اللي تحت وناخذ النيجاتيف entry له وناخذ اصغر واحدة. If this is done then the basic variable must be set to 0. Okay, so the optimality criterion says if the objective row of the tableau has zeros entries in the columns of labeled by basic variables، يعني يكون في عندي basic variable الأصفار and no negative entries columns labeled by non-basic variables، يعني هذول ما يبقى عندهم negative، كلهم يتحولوا إلى positive. Then we have reached the optimal solution. This is the optimality criterion. بكل بساطة بيقول لك اللي تحت يكونوا ما في عندي نيجاتيف منهم. اوكي الآن طيب كيف بدنا نوضح خطوات السمبلكس ميثود؟ رايحين نوضحها من خلال المثال التالي. I will go very quick over this because now you know the whole idea.
دكتور
ها راحت السكرين.
can you share the screen؟
اوكي يمكن صار عندي شيء خطأ. ايش عملت هنا؟ وين السكرين راحت؟
yes
اوكي كان في عندي ويندو. مش عارف ليش اختفت الويندو، كانت موجودة. هذه هي مرة أخرى. شايفينها الآن؟ بيضة. اوكي. Now everything is fine.
yes دكتور.
Okay. Now I will go so quick explaining why the methods we have seen give us optimal solution, and this will be combined with a simple example. Okay, now selecting the entering variable. Okay, selecting the entering variable proceeds from extreme point to adjacent extreme point. I already said that. From the definition of adjacent extreme point, it's clear that we reach such a point by increasing single variable from 0 to positive and decreasing a variable with positive value to 0. هذا اللي عملناه. Increasing كنا عاملين الفاريبل الاصليات اصفار صح بالانيشال سوليوشن لما عملنا 0 0 0 بعدين P1 all the way to Pm مش هيك؟ فالفكرة هنا الآن واحد من هذول نخليه يكون قيمة غير الزيرو وواحد من هذول نخليه يساوي زيرو وهذا بدنا إياه ينتقل إلى something does not equal zero. هذه هي الأيديا اللي بتكلم عنها اللي بدنا نحوله من زيرو إلى positive بنسميه entering variable بينما ال departing variable اللي هو هذا. اوكي now how to choose the departing variable. اوكي هذه البروسيجرز هي نفسها اللي انا ورجيتكم اياها لكن ايش هي الفكره هنا؟ شوفوا هذه هي البوينت الاولى اللي احنا بنبلش فيها 0 0 0 0 8 15 فرايحين نخلي الاكس الان ما يكونش زيرو هذا هو الاكس تمام لكن بالمقابل راح اخلي الفي هذا هو اللي يصير زيرو وهذا بدي اياه يكون something not zero. شو اعمل؟ راح اروح على المعادلات اللي فوق هذول واستفيد منهم. الان انا بدي اخلي واي تبقى زيرو معلش بدي اتعامل مع اكس. اذا انا خليت واي تبقى زيرو فهذول المعادلات بيصبحوا هيك تمام؟ الان العب فيهم شويه فبتصير اليو بهذا الشكل الفي بهذا الشكل. بدي اتخلص من مين انا؟ من في. ليش قررت اتخلص من في؟ لاني لو استبدل اكس في 3 بصير يو في 0. انا ممكن اتخلص من يو بصير في 0 ممكن اتخلص من يو لكن لازم اخلي اكس تصير 4 لكن اذا عوضت 4 هنا في بصير سالب مو مسموح لي اخلي شيء سالب. اذا راح اختار 3 هنا الاصغر لذلك احنا كنا نختار الاصغر. هذه بتعطيني x equals 4 وهذه بتعطيني x equals 3 لكن لو اختار الأربعة هذه بتخلي لي الفي تكون نيجاتيف لذلك كنا نختار السالب. ولهذا السبب احنا كنا ناخذ هذا ونقسمه على هذا وهذا نقسمه على هذا وناخذ الأصغر. ليش كنا نعمل هيك؟ لأنه كنا بدنا نخلص على واحد من هذول الفاريبلز ونحوله إلى زيرو من دون ما نحول الآخر إلى سالب. إذا عملية القسمة هذه لأجل أحول واحد إلى زيرو وأنا أخذت أصغر واحد لأجل ما أخلي الآخر يصير سالب. إذا فهمنا شو اللي صار. فهذه هي العملية هيك بتصير. فبننتقل الآن من إكستريم بوينت إلى إكستريم بوينت جديدة وبناء على إكستريم بوينت الجديدة هذه شايف هيها إكستريم بوينت 3 0 0 إحنا كنا عند الإكستريم بوينت هذه هنا 0 0 صرنا عند الإكستريم بوينت 3 0 0. ليش؟ لأنه حولنا الأحمر هذاك إلى 3 0 8 0 حولنا هذا إلى هنا. جميل؟ وبمثل هاي الحالة كان بصير الفانكشن لما نعوض x تساوي 3 شو بصير عندنا؟ هذا هو الفانكشن بصير 360. تحسنت قيمة الفانكشن كانت 0 بالأول كانت 0 تحسنت بالعملية هذه. راح نعيد هذه العملية لكن هذه المرة راح نقضي على u خليها 0 ونخلي y تاخذ مكانها. ماشي الحال؟ اوكي فهذه العملية هي اللي احنا بنسميها مرة أخرى departing variable bivoidal column و bivoidal row. عرفتوا مين هم وكويس إني شرحتهم من خلال الأمثلة. وإذا قرأتوا الآن هذا الكلام راح تكتشفوا إنه هو نفسه اللي شرحته the smallest non-negative theta ratio the largest possible value for the entering variable. The basic variable labeling the row where the smallest negative ratio occurs is the departing variable. Okay. Now إيش بقول لك هنا؟ If all the entries in the bivoidal columns above the row are above the objective row اخترنا bivoidal column. اوكي الآن إذا كل الانتريز لكن above the objective rows من دون objective rows إذا الانتريز بالbivoidal column instead of objective row are zero all of them are zero or negative then the entering variable can be made as large as we wish. Hence the given problem has no optimal solution. اوكي شفت الاوبتيمال فاريبل احنا على اي اساس قررنا انه هذا الانترنج فاريبل هنا هذا اكس يساوي 3 على اي اساس؟ اللي بنصفر فيه هي في صح؟ فاذا كانوا كلهم نيجاتيف كيف بدي اصفر هذه الفي؟ خلي اكس تكون ما لا نهايه ما بتصفرش عندي في وبالتالي بكون عندي no finite optimal solution. لهذا السبب في المثالين شفناهم فشلوا. الآن forming a new table. forming a new table. إيش عملنا الحركات هذه اللي عملناها؟ شوف الإكس راح تساوي هيك أو هيك. طيب شو اللي عرفني أنا؟ منين جبت هذا الكلام؟ أوكي جبته من هون. ماشي الحال؟ طيب أعوض هاي وين؟ الإكس بدي أتخلص منها، أعوضها وين؟ عفوا مين بدي أتخلص منها؟ في. أوكي وين مين اللي بدي أعوضه هنا أنا؟ الإكس عفوا. استفدت من هذه إكس شو تساوي؟ من اللي تحت أخذت إكس شو تساوي عوضتها باللي فوق، فطلع معي هذا الكلام. بعد ما طلع هذا الكلام رحت عوضته في ال Objective Function فأعطاني هذه النتيجة. هذه الحركات كلها بيكون هي عبارة عن الستيب اللي احنا عملناها. ماشي الحال؟ استعملت واحدة من المعادلات تعرف اكس ايش هي تساوي، ورحت عوضتها في المعادلة الثانية وعوضتها في الاوبجكتيف فانكشن، فبكون فعليا احنا بنعمل الحركات البايفوتنج. حركات البايفوتنج هي تمثيل لهذا الشيء. اذا وهذه الستبز اللي احنا عملناها locate and circle the pivoting intersection of the pivotal row and pivotal column. مثل ما كنا نعمل circle خليها تساوي 1 اقسم على k add suitable which is row the elementary row operation and d in the new table replace and label the pivotal row again entering variable. المعلومات الحركات اللي احنا عملناها اللي هي ملخصة هنا، يعني خلاص هذا انت سهل بالنسبة لك. لكن ايش احنا عملنا هنا؟ انتقلنا الى بالحركة الاخرى اللي عملناها بالبايفوتنج، ما وضحناها هنا معادلات، بنكون انتقلنا الى هذه الاكستريم بوينت. كنا احنا عند 0 0 بعدين رحنا عند 3 0 بعدين اجينا لعند هذه بعملية البايفوتنج اللي عملناها، وهذا هو مكتوب هنا عند 0 0 إلى 3 0 من 3 0 إلى 3/2 5/2. الانتقال هذا من هنا لهنا خلى الأوبجكتيف فانكشن يكريس تو 360 والانتقال من هنا إلى هنا 430. أوكي أتأمل هذا الشرح السريع هنا أعطاك فكرة ليش البروسيجرز تبعون السمبلكس ميثود هم بالطريقة اللي تعلمناهم. يكون بالسبب هو عملية تحويل بداية اختيار السلاك فاريبلز على انهم البيسك فاريبلز، بعدين تحويل واحد منهم الى نون بيسك وتحويل واحد من الاخرين الى بيسك. هذه العملية اللي فيها البايفوتنج كولومن والبايفوتنج رو. الغي هذا احوله الى زيرو، واحد من السلاك فاريبلز، واحد من الاصليين اخليه ياخذ قيمه غير الزيرو. هنا بكون تحركت من اكستريم بوينت الى اكستريم بوينت اخرى، ولاجل ان اعمل هذا الشيء لازم اعمل حركه اقسم هذا على الكولومن الاخير اقسمه على البايفوتال كولومن وخذ اقل واحده لاجل تخلي السلاك فاريبل اللي اخترته يكون زيرو من دون ما تخلي الاخرين يصيروا نيجاتيف، لذلك اخذنا اصغر واحده. بس نخلص يطلع معنا الجدول الجديد نعيد العملية مرة أخرى لأجل نحول سلاك فاريبل آخر من بيسك إلى نون بيسك، واحد من الأوريجينالز نحوله إلى بيسك بنفس الطريقة وبنستمر. فبنلاقي حالنا وصلنا إلى الحل بعد ما ننهي النيجاتيفز الموجودين بالأوبجكتيف رو، وبتكون هذه هي السمبلكس ميثود. والله يعطيكم العافية.